So for our first activity today, I'm going to turn things over to you all, and I'm going to ask you to try your hand at working another example from our OpenStax textbook. This is example 9.6 in the book, and it deals with applying what we know about calorimetry to solve a problem related to how an everyday object works, which is an instant cold pack. So in an instant cold pack, the reason your instant cold pack gets colder when you activate it, and here we're talking about a cold pack that you snap, not one that you have to store in the freezer, is when you snap an instant cold pack, you get a mixing between powdered ammonium nitrate, which is inside the cold pack, and an inner bag of water. So to activate the cold pack, you shake it up, you snap the water mixes with the ammonium nitrate, which is a water-soluble ionic compound, and the ammonium nitrate ionizes, breaks into its component ions inside the water, which is the solvent for the reaction. The reaction of ammonium nitrate dissolving in water is endothermic, and it makes the pack colder from the outside. So from your perspective on the instant cold pack, you're in the surroundings. The chemical reaction is the system. If you touch the cold pack or have the cold pack touch you, then you will feel the cold pack getting colder. So the balanced chemical reaction that applies here is 1 mole of ammonium nitrate, which has chemical formula NH4NO3 solid, dissolves in water because of water-soluble ionic compound, giving us NH4 plus and 1 mole of NO3 minus. So your ammonium nitrate dissolves in water to give you 1 mole of ammonium cation, 1 mole of nitrate anion. The question we want to deal with, example 9.6, is when this solid ammonium nitrate dissolves in water, the solution becomes cold. This is the basis for an instant ice pack. When 3.21 grams of solid ammonium nitrate dissolves in 50 grams of water at 24.9 degrees Celsius in a calorimeter, the temperature inside the calorimeter then decreases to 20.3 degrees Celsius. We would like you to calculate the heat flow value Q for this reaction and explain the meaning of its sign. So once you've calculated Q, check to see if your Q is positive or negative, and articulate as part of your answer what that means about the reaction. As you go through and work this, I'd like you to get out of just pushing through the math as fast as you can and actually slow down and practice writing out the assumptions you're making as you solve the problem at as many steps as possible so you can actually check your thought process, not just your math. What we're going to do with this is you can take as long as you want to solve this, but I'd recommend that you work on it for about 7 minutes. If your time's up or you get an answer that you're satisfied with, below this video you can find several other videos where I walk you through the solution. But I'm interested to see if you have developed your calorimetry skills enough to the point where you can solve this problem in a few minutes and work through the assumptions yourself. So give this problem a try. When you're done, check the videos below to see the correct answer and compare your thought process with mine. If you have any questions about how I get to my answer, this is an excellent thing to ask about during office hours or during the Zoom class time from 9 to 9:50, Monday, Tuesday, Wednesday, and Friday morning. So try it out. I'll see you in a little bit.